Hello everyone, I'm Altaf Bukhari and today we're going to discuss an introduction to shock and vibrations. First we're going to cover the following topics and then we will move to a MATLAB code where we will discuss certain type of phenomenon in different sorts of vibrating systems. Now let's move on with our topic. First of all, we have vibration. What is vibration? Vibration is an oscillation wherein the quantity is a parameter defining the motion of a mechanical system. An oscillation is the variation, usually with time, of the magnitude of a quantity with respect to a specified reference when the magnitude is alternately greater or smaller than the reference. So vibration is defined on the basis of oscillation. What is oscillation? That a body is oscillating about a mean position. Now, the magnitude can be greater than or less than the reference. But vibration is an oscillation in which quantity is a parameter defining the motion of a mechanical system. Let's move on with some examples of vibration in our daily life. First of all, we see a bullet train. And we have various vibrations occurring in vehicles. As we all know that in order to overcome these vibrations, we usually balance the masses. Then we have a man getting a motion sickness on a ship. Now this is due to vibration that our stomach feels upset. And due to certain vibrations, we can get useful work as well. For example, in this factory and this guy is rocking his baby's cart. Now, not all vibrations should be... now, we don't have to balance out all the vibrations to get rid of them. Some vibrations are good, they're useful to us. Now we have a few examples where there is a screw in an assembly line, and then we have cleaning of bolts in a certain liquid. We vibrate the liquid, which helps in cleaning the bolt. And then we have a man who is cleaning a pavement. Now, there are three basic components of a mechanical system: displacement, velocity, and acceleration. Now, for the force due to displacement, we have a spring constant. If we multiply the spring constant with the displacement, then we get the force needed. Then we get the force needed to push this spring. While in a damping system, we have the velocity function, wherein we use the damping coefficient c, and if we take a product of c and the velocity, then we get the force applied on a damper. While in the case of a mass, we have acceleration. So similarly, if you multiply the mass to the acceleration, you get the required force. Now, if you focus here, you can realize that if we take a time derivative of displacement, we get velocity. And if we get a time derivative of velocity, we get acceleration. So all of this is interconnected. Now we see the simplest form of a vibrating system. The simplest form of vibrating system is a mass spring system. Now we take an example of a mass attached to a spring. It is oscillating in the vertical direction. Now, what sort of frequency curve do we get? In the displacement frequency diagram, we see that we get one peak because there is one mass attached to one spring, and the wave obtained is sinusoidal. Then we see some relations of omega n, that is the natural frequency of the system, which is equal to 2 pi fn, where fn is the frequency, which is 1 over t, that is the time period. Now we move on to the topic of free vibrations. Now here we see that in the case of free vibrations, the mass is going downwards, then it's going to its mean position, and then to its extreme position. How does it happen? First of all, we apply some force, as we talked before, that this force must be equal to k times d. Now this force, when we apply it, for example, if we compress it, then due to inertia, it will go upwards to regain its original. Now, due to law of conservation of energy, this body will try to go to its mean position. And in doing so, it will go upwards due to inertia. It won't stop at its mean position, it will go to another maxima. Then it will come back to its mean position, and due to inertia, it will go back to the first extreme position that was downwards. Now this upward and downward motion gives us a sinusoidal curve. Now we know that when it is downward, it has potential energy, which is then converted into kinetic energy. And when it reaches its top position, it has maximum potential energy. Then it comes back with, now it has kinetic energy, and it keeps going downwards. Now both these energies are interchangeable. We have the relations for both the energies, kinetic and potential, and we use them to derive an equation for our frequency, that is 1 over 2 pi k over m square root. Now this relation is very useful to us. Now, for example, the displacement that we had, if we denoted it with small d, then the capital D is the magnitude of that displacement, and we'd use sine omega nt. This displacement will be equal to capital D sine omega nt. And from this, we obtain the same relation. Now, in the mass spring system, where we see the dotted curve is with, now we see two different curves. There is one dotted curve and the other with a solid curve. The solid curve represents two masses, while the dotted curve represents the first wave that we were discussing, the sinusoidal wave due to one mass. Now the dotted curve, if we take a look, we can easily see that it has more frequency, while with increasing the number of masses, the frequency has been reduced. The number of cycles per second is reduced. Why is that? Because in the formula of frequency, we have k over m under the root. Now, since m is in the denominator, if we increase the number of masses, then eventually the frequency will decrease. Now we have the second type of system that contains, now we have the third type of system that contains mass, spring, and a damper. Now we have these three basic components in all of the vibrating systems. If we want to convert them, all vibrating systems can be converted into mass, spring, and damper systems. Now we have a mass that is attached to one spring and two dampers with their coefficients as C1 and C2. Now, as we increase the dampers, the amplitude decreases. Why is that? Because an undamped system keeps on going upward and downward. There is no damping. Now, as it is damped, it won't go as high. It will be damped. Its motion will be constrained. It'll make a lower curve. So the amplitude will be decreased by introducing more dampers, and our system will become stable faster as compared to an undamped system. Now we have forced vibrations. Here the mass is attached to another spring and a damper. Now the force is being applied from downwards. The force is being applied from downwards. This is an example of forced vibrations. This is not a free vibration. We are applying a force from the bottom to make the mass move upward, so it keeps on rotating like this. Now, if we see the curve in the frequency domain, we observe that first we have a straight line, then we have a small peak, and then it keeps on reducing and eventually becomes zero. Now this small peak is small due to the damper. As we discussed earlier, that a damper damps out a system. It reduces the amplitude. Now if we remove the damper, we'll get this curve, the dotted line. And the phase angles diagram is also given. First it will be 90 degrees, and then as it goes upward to make the peak, it will become 0 degrees, and then it will go back to the 90 degrees. Now we have response combination. Here we have two different systems. Here we have two masses and it is a forced vibration because the force is applied from downwards. Now as we move on, we see that the first mass, capital M, is attached to a damper and one spring that is directly in contact with the surface where the force is being applied, and another mass is applied upwards. Now this mass has its own spring and its own damper. Now the first mass causes the dotted line on the magnitude frequency diagram. If you notice, there's a dotted line, there's a peak going upwards, and then it keeps on reducing, which will eventually become zero. And the second mass is that light color, the line that is really light, not the first peak but the second peak. There we have a system that is going easily, smoothly, and then we have a damped curve which is eventually going towards zero. Now when we see the combined effect of both these masses, we obtain these two curves, these two different curves in the same diagram, because it is one system with two masses with different, what can we say, with different graphs. Same goes with the phase angle diagram, phase frequency diagram. First it'll be phase angle will be 0 degrees, and then it'll fluctuate to minus 90 degrees, and then it'll go to minus 180. Now this is the combined effect of both of them. But if we see the first mass only, its phase angle will be changing from 90 degrees to 0 degrees to minus 90 degrees. But since we use the combined effect, we have this phase angle diagram. Now we have a response model of a single degree of freedom system and a multi-degree of freedom system. In a single degree of freedom system, we have one peak because there is one mass. But in a multi-degree of freedom system, for example, a car, we get multiple peaks that correspond to each of the mass attached in the system. Now we have a real-world example. There is a foundation and two bearings on the top attached with a damper and a spring each, which are then attached to a rotor. Now, due to the motion, we will get a similar diagram that was in the multi-degree of freedom system. Here we have basically four different masses, and we have many dampers. We have four dampers, five dampers, and five springs attached to them. So we will get multiple curves if we look at its magnitude frequency diagram. Now we observe the relationship between forces and vibrations. First we have input forces, then we have system response, that is its mobility, its motion, and as a result we get vibrations. We have forces, we have system response, and as a combined effect of the applied force and the system response, we get vibrations. Now, forces may be caused by imbalance, shock, friction, or acoustics. Mostly, the vibrations in our systems are due to unbalanced masses. Due to these unbalanced masses, we get relative motion, and this relative motion leads to vibrations, which leads to the failure, earlier failure than expected one. So we try to overcome it by balancing out those masses, or sometimes there are initial condition problems and we face them forwards to reduce them, and then we have eigenvalues, but we won't be discussing them here. Okay, so the structural parameters, there are three basic structural parameters. As I said earlier, there's mass, there's spring constant or stiffness, and then there's damping. All the mechanical vibrating systems can be converted into our required systems of masses, springs, and dampers. And then we have three basic parameters that we discussed earlier as displacement, velocity, and acceleration. Now we will take a look at the relations in the following slides. Now, why do we measure vibrations? To verify that frequencies and amplitudes do not exceed the material's limit. Now, if they exceed the material's limit, then we will get failure or fatigue. To avoid excitation and of resonances in certain parts of a machine. Due to resonances, the vibrations will be further increased and will be a cause of even more problems. To be able to dampen or isolate the vibrating sources to make conditional maintenance on machines, or to construct or verify computer models or structures. Now we move on to the type of signals. Basically, there are two main types of signals. There are stationary signals and then there are non-stationary signals. In the stationary signals, we have further two more types. There's deterministic and then there's random. And in non-stationary signals, there are continuous signals and transient signals. Now, what does stationary mean? It means standing still. It means not changing too much. Now, in the case of deterministic stationary signals, we have similar signals that are progressing at a constant rate. And in random signals, we have, for example, here we are given the example of a rainfall. Now, in non-stationary signals, there is no continuity. First of all, we have this example of a man that is drilling a pavement. Now, there is nothing stationary about this. He is not doing it in a continuous manner. Sometimes more force is applied, causing greater vibrations, and sometimes it's lesser. Or when we hit a steel object with a mallet, we get a transient response that happens just for once. You strike it, there's just one response, you get a few curves, and then it's a straight line all over again. Now let's move on to deterministic signals, and we have a very important example of a gearbox. Now, in a gearbox, there are certain parts that are arranged at our specified places. Now, if we try to look at its amplitude time curve, we see that the amplitude time curve seems to be in a continuous manner. It is stationary and it is deterministic, as explained earlier. Earlier, we were looking at another example of gears, but now we have a gearbox. And if we look at the amplitude frequency diagram, we have a few peaks showing that there are more than one masses attached together with certain components including springs and dampers. Now let's move on to the next slide with deterministic signals and harmonics. Now we have three different types of graphs. In the first one, we have two different types of waves. First, it starts, and then another one starts from the bottom, taking it upwards. So we have two different frequency curves. But in the second diagram, there is one wave, one sinusoidal curve, showing us that there is only one system, there is only one mass that is causing these fluctuations. And due to its higher time period, due to its lower time period, we get higher frequency. But as the time period increases, frequency decreases because frequency and time period are inverse of each other, are inverses of each other. Now, in the third figure, we have a single sinusoidal curve. But if we look closely, we will observe that the frequency is double than the frequency in the second figure. And just like that, on the frequency diagram, we see that the frequency is plotted twice at a distance of as compared to the second figure. So that's why we have f1 plus 2f1. In the second figure, we have f1, and in the third figure, we have 2f1. So if we look closely, if we combine the effect of both of the lower figures, we will get the above figure. If we take the second and the third system as a combined effect to get one frequency diagram. We will get the one on the top. Now moving on, we have harmonics, and we see that there are signals traveling, and then we see what sort of frequencies they might carry. And as we move on, we have the example of a random signal. Now in a random signal, this is the form of a stationary signal. We are given the example of rain. It is coming in the same direction. The rain pours at the same direction, but there is no continuity in the amplitude. Sometimes it's more, sometimes it's less. So we get a frequency diagram that is disturbed and curved. Now we move on to impact or impulse shock signals. We are shown the examples of a cannon being fired or a beam being hit by a hammer. On the time domain, there's just one peak. For example, when the cannon is fired or when the hammer is hit, we get one peak and then it settles down and then we get a flat line. Just on the frequency curve, we see that the irregularities are less than as we observed in the previous diagram. Now we look at the important time signal parameters that we use in our calculations. First we have the peak value, the topmost value, then we have peak to peak value, that is we see the above peak and the bottom peak, and then we have the average value, we observe the root mean square value, the crest factor, periodicity or repetition rate, and then we see the duration. Now here we are explained what these are. The peak value is the first peak, the highest peak obtained from the mean position, while peak to peak value is the maximum peak on the positive side and the maximum peak on the negative side, and we take its total length. And in the average, we go from mean position to extreme position and we take its average. And in the root mean square value, we take the mean, then we square it, and then we take its square root. Then we have the relations that are used to obtain RMS, average, and the crest factor. Now we have two different systems and we're going to differentiate between them. What is a linear system and what is oscillatory system? In a linear system, we see the motion in a straight line, while in the oscillating system, the body moves forward, then it comes back to its mean position, it goes back to the second extreme position, comes back to the mean, and goes back to its first extreme position. Now, the motion of an object along a straight line can be described in the form of an instantaneous position, its velocity at a given time, and its acceleration at that time. For an oscillatory motion at a certain frequency, the three parameters are strictly linked together. What are the three parameters again? Displacement, velocity, and acceleration. Now, as we observed earlier that the time rate of displacement is velocity and the time rate of velocity is acceleration. These are simple conversions. We take the first relation that we obtained from the displacement diagram, that displacement is equal to the magnitude of displacement and the sine of natural frequency and the time. D is equal to capital D sine omega t. And then we take its time derivative, we get velocity, and by obtaining the second time derivative of the displacement, we get the acceleration. And we have these curves to match the obtained relations. Now we have conversions using a nomogram. Now, nomogram is very important for certain conversions in a vibrating system. We have units of vibrating signals, that is, acceleration is meter per second square, velocity is meter per second, and displacement is measured in meters. and we have their conversions also given to us in the next column. The measurement chain. We have transducers, then we have preamplifiers, then we have filters, then we have detectors or averagers, and finally we get our required output. All of this system works in a chain from the left side to the right side. Here we're given an example of a garbage disposal system where garbage goes in and then it works and then the garbage goes out, the processed garbage. Now this is also an example of the measurement chain. This is a chain process. Now we conclude what we discussed till now so that we can move forward to the next portion of our presentation. The fundamental nature of vibrations, and we discussed the mechanical parameters involved. We discussed the types of signals that we encountered. We saw their types, we discussed them, we looked at their graphs, and we then saw the relationship between acceleration, velocity, and displacement, and we saw their conversions. We saw the units, and we saw the different conversions of those same units. And we, in the end, just now, we saw the importance of a measurement chain, where we have a chain process. And now we move on to the next part that helps us understand the vibrating systems with the help of MATLAB. Now we have this MATLAB code given to us, and in a simple mass spring system, 1 degree system, and we earlier discussed this system, how it works and how the force required at the spring will be K dot D, and at mass we will have M dot A. With the mass we will require acceleration, while with the spring we will need the displacement. Now the basic equation is given that mx double dot plus kx is equal to 0. Now x is displacement, x double dot means 2 times time derivative of displacement, which means acceleration. It's the same thing. Mass with acceleration is equal to a force at the mass, and then at the spring we have the force that is equal to k times displacement. Now k is the spring constant. Then we have omega n, the natural frequency, k over m under the root, and then we discussed what happens if we include two masses. If we increase the mass, the frequency will decrease. Then we have the relation where x of t is equal to a sine omega n t plus phi. Then we have the relation for x of t. Now we can play with the parameters here and we can obtain these three curves. For initial displacement is equal to 3 and initial velocity is equal to 2. Now we have three different responses. During the first response, mass is equal to 1 and damper is equal to 5. Now, m is equal to 1, spring constant k is equal to 5. Now we have the value of mass and we have the value of k. And we know that frequency omega n is equal to k over m under the root. Now k over m here would be 5 square root. For 5 square root, we get a graph, a sinusoidal wave. It has large frequency. And now if we look at the second response, it is for m is equal to 5 and k is equal to 5. That is, k over m will become 1. Square root 1. Now as the mass increases, k over m decreases. As k over m decreases, the frequency, the natural frequency, decreases. And so we have the second graph where the frequency is decreased as compared to the first one. And then in the third graph, the mass is even increased further. Now m is equal to 10. Mass is further increased and the frequency is further decreased, as we discussed earlier in the previous slides. Now moving on to our next system, we have a damper, a spring, and a mass. Now, all three components in the same system, since damper is introduced, we already discussed that if we introduce the damper, then the amplitude will be decreased, it will be damped out, which will be easier to note from its curve. Now we see that as we increase the damping coefficient, the amplitude of the wave decreases. In the first one, we had one system and it was damped, but we increased the damping coefficient and its amplitude further decreased. And then we have the third system where its amplitude has even decreased further. Now zeta is omega n is the natural frequency and zeta is the damping ratio. Now as we increase the damping ratio from 0.05 to 0.1 and then to 0.5, as the damping ratio is increasing, the amplitude keeps on decreasing, as can be observed from the given three figures. Now we move on to its relations. Here we have mx double dot plus cx dot plus kx is equal to 0. As we discussed earlier, with the mass we will require acceleration, that is x double dot, and with the damping coefficient we will need velocity, that is x dot, and with the spring we will need x, that is displacement, with the spring coefficient k. Now there are three different forces, we take their sum and we put them equal to 0. From that we get the relation for zeta, the damping coefficient, and if zeta is greater than 1, then the system is overdamped. If zeta is equal to 1, then the system is critically damped. If zeta is less than 1 but greater than 0, then the system is underdamped, which is mostly the system that we work with. And if zeta is equal to 0, then the system's undamped, because the damping coefficient, because the damping ratio is 0, there is no damper. If there's a damper, there will be a damping ratio. Now we see at zeta is equal to 1, the system is critically damped. We see that we have a straight line going downwards, which eventually becomes 0. Now in the second figure, we have an overdamped system with damping ratio equal to 5. Since the damping ratio is equal to 5, it is even further damped, and as we move forward, there is a straight curve. It's smoother than the curve that we observed in the first figure, and the smooth curves become 0. But in the third figure, zeta is equal to 10. It's even more damped. We already have an overdamped system, and now the damping ratio is even increased. So the curve going towards 0, the decay, the decay towards 0 is even smoother. It goes straightly to become 0, to become completely damped, to have no fluctuations. Now we discuss the next slide, where we see that if we remove the damper in our previous discussions, in our previous figure, harmonic excitation of undamped single degree of freedom systems, we have harmonic excitation and the system is undamped. Now mx double dot plus kx is equal to f naught cos omega t, where omega is the driving frequency. We have these relations that if we remove the damper, then how we can observe the relations. Now, first of all, we had omega d is equal to 5 and omega n is equal to 7. Then we saw some fluctuations with not much frequency. But if we increase the omega d value to 20, then we see similar fluctuations, but the frequency has been decreased, the frequency has been increased. And now for the third response, where we even increase the value of omega d, then the frequency is very much increased. We see that it looks like a single curve, but there's a lot of frequency in that curve. Now we move forward to the beats. Now what happens that, for example, in the case of an earthquake, let's take another point of view of these three figures. Now, as the first figure shows that the mass is greater. For example, the motion of a train, or let's say a truck. The motion of a truck. Now there is greater mass, so there's less speed, so there is less frequency. Now from a truck we come to a bus that is lighter than the truck. Now as the bus moves, the frequency will be higher, but because its mass will be lower. But in the third figure we see that the frequency is even increased. So let's suppose that this is the motion of a car. The mass is smaller, so the vibration will be greater, because we saw that frequency is, the natural frequency is equal to k over m under the root. So as m decreases, the natural frequency will increase. And in this figure we have the phenomenon of beats. Now what is beats? For example, in the case of an earthquake, there are several frequencies produced, and the ones that have similar magnitude, they resonate with each other, and the frequency, it keeps on increasing due to resonance, and it keeps on growing bigger, and within no time our part will fail. Now we have an example of beats phenomenon. First we were looking at the response of a single beating phenomenon, and here we have multiple beating masses. Now we move on with the same system that we were discussing earlier, only with the addition of the damper. Now the equation will be mx double dot plus cx dot plus kx is equal to f cos omega t. So the relations will change relative to the damper that is introduced in the system. Now we see that zeta is equal to 0.6. Zeta is equal to 0.06. The damping ratio is 0.06, and with that we have a certain frequency, and as zeta keeps on increasing, the frequency keeps on increasing, and the amplitude keeps on decreasing. Now in the first three figures. Now in the next three figures we see that the similar behavior, as zeta keeps on increasing, the amplitude is decreasing, and the natural frequency is corresponding to the masses, as we have discussed in detail in the previous slides. Now the first figure is of a single mass, while the second figure is of both the masses. Now we have the same system that we were discussing earlier, but in the vertical direction. Let's discuss more about it. First, we see the important relations that we obtain from the system: harmonic motion of the form y of t is equal to capital Y sine omega bt. We get the value of a naught and phi. This phi will be the phase angle. Now we convert the parameters and we observe the pattern that is shown to us in these figures. Now these slides are quite similar to the ones that we have discussed earlier in detail. We are just playing with the parameters, we are increasing, if we increase, for example, the damping ratio, then the amplitude decreases, and if we increase the mass, then frequency decreases. And we have similar functions here where we are playing with the similar parameters. Now in this figure we see in a state space, it is shown to us in a state space form that the damping is increased, and so if the damping increases, then our value of our amplitude will decrease. Thank you guys, that's enough from me, and I'll see you again next time. Thanks.